Hi, this is Roger from Labs. Today with a little explanation what 4-terminal connections or Kelvin connections or Kelvin clamps are used for and how they work and how you can implement them by yourself. In the last video I noticed that this little battery charge tester, which has a provision for a 4-terminal measurement, which you can see here, it has extra clamps for measuring directly at the battery under test, that there was something wrong with how they implemented the 4-terminal measurement. In the meantime, I've already found out exactly what it is, and I will explain this and how to solve the problem with probably quite an easy mod to this circuit in the next video. But before that, not all of you know how 4-terminal measurement works and what's it good for and where it is used. And so this will be a little tutorial which also belongs into the category precision op-amp measurement. So let's make a little drawing and see what the basic principle is. Now imagine you have either a current or a voltage source, it doesn't matter, and you connect this current or voltage source to your circuit, which could be a multimeter or anything else. So usually this here at the negative edge will be your local ground. But of course you have the resistance in the leads and contact resistance, etc. Let's add them up here at one resistor, which adds up all the resistances on the lower side, and of course you have the same on the upper side. So let's call them, well, RU for upper resistor and RL for lower resistor, and this here is your device under test. Now if you reference the voltage measurement of your device under test, which could be, for example, a shunt resistor for measuring the current, if you reference it to your local ground, you will have at least here the lower resistance from your local ground to your device under test. And if you also tap off the voltage here at the upper point, you will additionally have the upper resistance. So what's the remedy for this? You make a measurement directly at your device under test, but now comes a problem. You can't reference this voltage measurement here to your local ground. You have to take the true difference between the voltage here on the upper side of your device under test and here on the lower side of your device under test. And therefore you need a circuit that calculates exactly the difference voltage. And this is typically what is called an instrumentation amplifier, which has a positive input, a negative input, sometimes also a provision to external connections to set the gain. And this builds the difference between U plus and U minus, and if you have an external gain, multiplies it with your gain factor. So I think the principle becomes clear. Now let's first of all take a look how such an instrumentation amplifier is implemented and what applications there are, and there are a lot of them, to use this principle of 4-terminal connections. Now why are there 4? You have 1 and 2, where your device under test is connected externally, and you have here, these are the Kelvin connections. I'll abbreviate them with KC for Kelvin connections. These are the connections which directly tap off the voltage of your device under test. And some examples I've prepared. We already saw this little battery tester which made it the wrong way, although you have your 4 terminals. That's not really how it should be done, how they made it to work here. But you can see an example of what I call, for example, Kelvin clamps. Here from my LCR meter from Mastec. This is the connector. You see, this is a PCB connector, which is put into the meter. And you can see one side is the shielding here. And then these two are the connectors for the two clamps. And there are two wires, or including the shielding, 3 wires going to each clamp. You can see a yellow one, a red one, because this is a 2-layer PCB. And so they are not connected, the upper and the lower side are not connected, except of course here for the shielding. And so they come in here, although you can't see it directly, but where you can see it a little bit better is with my home-built milliohms adapter. Just try to refocus it. So here you can see really the 4 wires, 2 for each clamp. And you can also see how they are usually called, the sense wires. These are the Kelvin connections. And they arrive here, and you can really see that there are 2 cables, no shielding in this case. And one goes to the upper jaw and one to the lower jaw. And if you clamp this to a component or to a wire or whatever, then the voltage is tapped off with a sense wire here directly at the lead of your component. So that's how you can make milliohms measurement, and it's probably the only way you can do it the right way. And this one is, for example, quite useful for locating shorts on your circuit, and therefore you need these 4-terminal Kelvin connections which end in Kelvin clamps. So let's go back and see how such an instrumentation amplifier works and how you can build your own. And for example, at the first application, just for measuring current. So before I start to explain how this is really done, the current and resistance measurement is basically the same, as we will see in a minute. I forgot to mention, why is this called Kelvin connections, or why are these devices that I just showed you named Kelvin clamps? They have nothing to do with the temperature scale of Kelvin, but all of them are named after Lord Kelvin, or with his civil name William Thomson, who was one of the most prolific scientists and engineers of the mid and late 19th century. He was a contemporary of James Clerk Maxwell, of Michael Faraday, etc. And he certainly belongs into the top 100 of scientists of all times. You should read his biography, for example, in Wikipedia, etc. It's very interesting what he all was researching about, what he invented, etc. So many things are named after Lord Kelvin. And so that is about the naming, why these are called Kelvin connections. Now, let us suggest we have a current source. It doesn't have to be a constant current, but anyway, a current source. And we lead this current to a resistor. This resistor could be a shunt resistor, and then we of course have our normal way of measuring currents like in a multimeter. You have your external current of unknown value. You lead it through a shunt resistor, and then you tap off the voltage at the shunt resistor, and the voltage is proportional to the current, and of course according to Ohm's law, the current is the voltage at your shunt resistor divided by the value of your shunt resistor. So that's the normal way of measuring currents. But the same principle applies how you measure resistors. Then you just reverse it. You have your current source, in this time a constant current source, inside your multimeter. You have an external unknown resistor under test, and again the voltage here tapped off directly at your resistor under test is in direct proportion to the voltage you tap off, and then your resistor under test, the value, simply becomes the voltage at your resistor under test divided by your constant current that comes or is generated inside your multimeter. So it's the same principle, but in both ways of measuring, we have to tap off the voltage directly at our resistor, otherwise we would measure, and again here we have our upper and lower unwanted resistances coming from the ohmic resistance of the test leads or the PCB traces, and of course any kind of contact resistances. So to get rid of that, or for not getting a false measurement, as we already know, we have to measure here the difference between the upper and the lower point of our device under test. And of course we have to do this with a very high input impedance, because the current may only flow through our resistor, and if we would have a low impedance path here, then we of course would get a false result. So how do we do this? The simplest way, and that is also the simplest way to build up an instrumentation amplifier or a true differential amplifier, is we just put two op-amp buffers, usually with FET inputs, on both terminals of our resistor. And so the first task is achieved, measuring the upper and the lower voltage with an ultra high impedance in the gigohm range. And then we of course need still a circuitry for, in an analog way, with an op-amp, building the difference between these two voltages. And the classical way looks of an op-amp circuit that builds the difference looks this way. You first have a voltage divider on your positive terminal of your third op-amp, and it becomes a little bit awkward. And on the negative input, you make it this way. Now we have two voltage dividers, and let's call the resistances here R1, R2, R3, and R4. And this is the classic circuit for building a difference between two voltages. And you can see the two inputs of this op-amp circuits have a relatively low impedance. Here it is R1 plus R2, and here it is R3 in parallel to R4. This would be the input impedance of the two terminals here. And of course, if R1, R2, R3, and R4 are not in the megohm or gigohm range, which would be impractical, we cannot connect this directly to our resistor under test, because then we would get here currents that disturb our measurement result. So that's why we need the input buffers here. So, and what we have to watch out for to get really a correct result is that the ratio of R1 to R2 must be exactly the same as, or as good as possible, as the ratio of R3 to R4. So we have to match the ratio of these two resistance pairs as good as possible to get what is called a high common mode rejection ratio, because here the voltage here could be anything. It could be plus 1 volt here and plus 1.01 volt here on the upper side. It could be plus 5 volt and plus 5 point something here. So to get always the correct difference here at the output of the third op-amp, these two ratios must be matched as good as possible, and the gain is simply R2 divided by R1, which is the same as R4 divided by R3. And so if you make them all equal, the gain would be exactly 1. And making them all equal is a good idea, because then you only need one kind of precision resistors. Or for example, if you take a bunch of 10K resistors, you can match them with your multimeter. You just pick out 4 of as good as possible same value, or at least 2 pairs of the same value, and you would get what you desire: a high common mode rejection ratio and a gain of exactly 1. So this is the easiest way to build up an instrumentation amplifier. Of course, here you have a fixed gain, which is given by the resistance ratios. To make a variable gain in integrated instrumentation amps, there's usually a slightly different topology chosen, but that is the easy way to build up an instrumentation amp with 3 op-amps and a fixed gain with resistors you can get anywhere as long as they have equal ratios. And you could even simplify this. When you measure really current, you know that your shunt resistors are of very low value, usually in the milliohms range. For example, at your 10 or 20 amps range of your multimeter, you usually have a 10 milliohm resistors. Now there you could of course leave out the 2 buffer op-amps, the unity gain op-amps, because if you choose resistors here in the 10K range, the current flowing through them is so negligible compared to the current flowing through the shunt that you wouldn't need the unity gain buffers here. On the other side, because at a resistor, at a shunt resistor with only milliohms resistance, you can imagine that the voltages here are also in the millivolts or even in the microvolts range. So you need, of course, precision op-amps with a very low offset, so otherwise you would not get the correct result at the output, but you would more or less measure the offset of the op-amps and not a value that is proportional to the current. So now you probably would come up with a question: well, if we have a 10 milliohms resistor here, how can I tap off the voltage directly at the 10 milliohms? Because even a 1 millimeter PCB trace would give more than a 1% error, or the solder connection, the solder junction would also be could be many milliohms and give you totally wrong results. Where there are special 4-terminal shunt resistors, I will show you one in the background, which have these tap-off Kelvin connections integrated directly at the resistive element. So it doesn't matter what's on, how much extra resistance is here on the outside where you solder it, because they are really, that would be better to draw them than this way. The Kelvin connections are directly connected internal to the precision trimmed resistive element. So that's the basic principle. You have a current path through your device under test. You tap off the voltage directly at your device under test, put usually 2 buffers and a true differential amplifier, or you get, of course, ICs that combine all this circuitry, and that is called an instrumentation amp. And then you have here on the output a voltage that is not referenced, or that is referenced to your local ground, which is usually something else than the point here. It's on another voltage potential due to the action of here the PCB traces and everything we have here. And so the differential amplifier or the instrumentation amplifier basically references any voltage that you measure anywhere in your circuit, it references it to your local ground and you get a low impedance output. Now there is a third way how these Kelvin connections can be used, and that is the principle: how do you measure the internal resistance of a voltage or current source? And that is what this little tester here basically had, this Kelvin connections, because here you can see you have a milliohms display, or you can by turning the knob set your display to display the internal resistance of your battery under test. And let's see, as the last example, how you can make this by your own and how they tried to implement this here with this tester. So you quite often want to know what's the internal resistance of your voltage or current source. This could not only be a battery, it could be a lab power supply, it could be your power amplifier, then of course it would be an AC voltage source. It could be anything, and because by definition the internal resistance is something that you can't directly tap off, how would you want to make it with a battery, for example? It's just the ohmic and chemical and electrolytical resistance inside the chemistry of the battery. You cannot measure this the easy way, so you do it with a trick. You just connect this with a load. This could be a simple resistor, it could be a constant current load, whatever. And then you of course get a load current. But now comes the problem. We again have our resistors. So if here is where you want to put your multimeter in, you don't measure the internal resistance. You always have again your upper and lower lead and contact resistance and whatever. So again you make Kelvin connections here and you measure the voltage here again with an instrumentation amp. And now comes the trick. At the same time you have to measure your current with an amps meter. And now with our little battery tester, how did they do it? Well, they first, because the load resistor or the load transistor here can be switched off by the software, you first of all measure the voltage without any load. And that you can do at whatever place, because if no current is flowing, the contact and the lead ohmic resistance, they don't come into play. So the no load or open circuit voltage, that is no problem how to measure them. But as soon, and that is your first voltage, let's call this, well, we will note it down later. So we have a first measurement with current 0 and the open circuit voltage. And now we switch on either our load resistor or our constant current load, whatever, and we get a second result. We get now a current plus a second voltage, and of course, due to the action of the internal resistance, the voltage here measured directly with Kelvin connection with an instrumentation amp. And here we have our voltage measurement. We get now a second voltage with a load. But here you can see it's very important to have this instrumentation amp directly connected with Kelvin connections at your source, because otherwise you would measure the internal resistance plus the upper and lower ohmic resistances. So, and now how do you calculate the internal resistance? Well, so now all in all we have 4 measurement values. We have our open circuit voltage measured as V1. We have our open circuit current, which is of course 0, because it's open circuit or no load. And then we have our underload voltage V2, which is of course lower than V1, and we have our underload current I2. And now the internal resistance is simply the difference of the two voltages divided by the difference of the two current. Because the open circuit current is 0, we can leave out this minus I1, and that would simply give delta V, the difference of the two voltages, divided by the current under load. But I did note this I1 here because there's a second way. You could also measure your source with two different load currents, because sometimes it's not practical or even not possible to measure the open circuit voltages. So you just take two different load resistors or two different load currents, and you simply take the ratio of the voltage difference divided by the current difference. So quite simple as that. And that's a good exercise in working with Ohm's law. You should perhaps think about yourself how this formula is derived. It's quite simple, but you can see how universal Ohm's law is, what you can do with it. And that's the easy way to measure the internal resistance of voltage or current sources. Just difference of voltages divided by difference of currents. So that was it for today. If you liked it, then please give it a big thumbs up, and see you next time, where we will try to fix this little battery charge tester and take a look at what they made wrong with their Kelvin connections and their 4-terminal measurement. So thanks for watching. Until next time, bye from Roger, bye from Kanka Labs.